somebody else? I just want to raise this a bit, so just make sure it doesn't drop. Yeah. Yeah, for what?
So I just have Gatecore, and I don't think I'm registered in any tutorial sector for this course.
Oh, okay. You're not? Oh, how come?
Yeah, I'm not registered. I don't know, for some reason when I was choosing the course, I didn't see the tutorial section.
Oh, then what do, but have you been attending one of them?
Attending one of them.
Yeah.
For the exam,
No, no, not at all. It has nothing to do with marking.
I still want to pick up my paper though. Like,
Yeah.
I'm not gonna.
Yeah, well, we're going to find a way to do that. For those of you who do not pick it up from the tutorial, I'm sure I have a big stack, right? I have to find a way to get some TA and maybe some fixed hours that you can contact the TA and so on. I have to make arrangement for that. Yeah. Depending on how big the stack is, I guess, yeah. I can bring it to class if it's small enough, but then if it's big, then I'm not going to do it. Maybe me, maybe someone else, yeah, depending on how big the stack. Yeah. Let's get started. Okay, let's get started. Screen. So we are all done with unsupervised learning, and I know that during the last 2 weeks when we cover unsupervised learning, many of you are a bit busy with other things, so you might be a bit behind with that. So, but everything is online. Hopefully, the recording is okay. Yeah, most audio and the slide, and then we're going to slow down a bit for the tutorials. We're going to split this tutorial of unsupervised learning into 2 weeks. What you already have one, some of you this morning, and then next week we also be on unsupervised learning, which is the EM. Yeah. So this week would be K-means GMM. Next week's EM. Okay. So hopefully that will give you a bit more time to catch up if you need to. Yeah. But meanwhile, for the lectures, we have to move on to the next topic. Okay. So which is the famous SVM. Yeah? Okay, support vector machine. Vector. Come on. SVM. And first of all, it was developed in the 1990s. Okay. And remember when we talked about linear classification, there was this issue of those lines. There are infinitely many lines that can separate our data, right? But how do we teach the machine which one is better? We know that some of them will be better, yeah? The ones that be further away from the data points, right? So that question would be call them L1 and L2, just give them a name. Yeah. But intuitively, we prefer L2, right? It's further away from the points. Why is that? Why do we prefer a line that's further away from those points? Yeah.
Further away from the points, the more confident we are that they're.
Yeah, safer. Yeah, safer to have a more cushion for errors. Yeah, in case these points are some I cannot talk today. Perturbation by noise. Yeah, yeah, a bit noise in the measurement. Then we are safer to use a line that's further away from those points. So intuitively we understand this very well, right? So in other words, if I look at the distance, I draw a circle from that tangent circle, right? That's how big the circle is. And this one, I have a safer margin of error. Yeah, this point can be perturbed more, and I still have the correct classification, right? Yeah. So we expect that E out in terms of the test error, the second line will be better. Yeah. Is I say at least more robust. Yeah, for the purpose of E out or generalization. Yeah. And robust to say data noise. Yeah, let's say against data noise. So the question is, how do we tell the machine the second line is better, right? Yeah. Yes.
Sorry. Doesn't linear regression? Sorry, not logistic
Logistic regression. Yeah.
Basically.
Yeah, that's right. Logistic regression is one way to do this. Yeah. But even logistic regression is a bit hand-waving. That yeah, sure, you have that cross entropy and so on. It's not very exact. There's no exact guarantee. That SVM can give you, as you will see. Okay.
So what I'm noticing is that on the left, the points are, I guess, closer to the line. So should we maybe measure the closest point to the line, and then,
Yeah.
And then I guess the longer that distance is, the better the line
Yeah,
is.
yeah. The closest point to the line, and then that distance of the closest point to the line. Yeah. The longer distance is better. Therefore, that distance of the closest point is our main performance metric.
I guess that's why it was one of the past papers. I guess that's why the distance was on one of the past papers of the midterm.
Well, yeah, but anyway, now we'll see how to calculate this distance, okay? We call this the margin, yeah? The distance of the nearest point to the line is called the margin of this line, okay? So, so-called classifier margin. To define that, well, again, let's look at our data set. X1, Y1, So we're going back to supervised learning now, right? Although SVM can be applied to unsupervised learning, by the way, but we don't talk about it here. RD, and then YN, of course, since we can say binary now, this. Yeah, this is for all data points. Yeah, for all n. Our decision rule is still the linear classification, so binary as well. Yeah, so sign of W transpose X, except that we write out this form that's unaugmented. Okay, we do not write the augmented form anymore for SVM. Right? Just for by convention, it's also later you see mathematical convenience. Yeah, so now W is actually d-dimensional vector. Okay, not d plus 1. Yeah. But previously, when we do augmentation, we just say that this intercept B is using B times 1, right? And so B is actually W0, and then 1 is X0 in our previous augmented form. Yeah? Same as before, except that we do not use augmented form here. Yeah? Just, maybe let's write it out. No, we do not use augmented form here. We do not use so now our line hyperplane if you want, yeah, in a higher dimensional space. But let's just call it L still anyways, yeah? Just a line, yeah, even though it's a plane, could be. Is simply this one equal to 0, right? That's our line, right? And this is so-called decision boundary. Is the decision boundary. And we want to find a decision boundary that's good in terms of the so-called margin. So the distance, yeah, now therefore we have to find the formula to express the distance of any data point to this line. Yeah, so that's the next thing.
Why are we not using the augmented form in this case?
Just for convenience, you will see the math looks much cleaner without the augmentation. So, what is the distance? From some data point xn to this line L. Yeah. So let's draw a picture in two-dimensional space. As this that we can do, right? In two-dimensional space, it's actually things a bit easy to see. So let's say this is your line, like that, and let's say this is your point, xn like that. Okay. What do we mean by the distance of this point to that line? Well, high school stuff, right? You draw a perpendicular line to the line, yeah. That's the perpendicular, yeah. And the length of this dotted line will be the distance of the point to the line, right? If this is a hyperplane, you do the same thing, yeah. Just draw a perpendicular line to the plane. That's the distance. Okay. So the question is, how do we mathematically express the length of this line? Yeah. Okay. So we need a few facts. The first one comes from your linear algebra course, if you have seen that before, which says that W, this W, yeah, in this line, Wx, that W, in this unaugmented form, is a vector that's perpendicular to the line. Yeah. W, in fact, is in the direction that's perpendicular to the line. Prove it, yeah, but we don't do it here. Yeah, it's just kind of something that one learns from linear algebra. Okay. But again, this W has to be unaugmented form. Yeah. If it's augmented, then it's not linear in the same space, right? It's a two-dimensional space, so it has to be an unaugmented form. Then W is perpendicular to the line. Yeah. Then let's consider any point if we draw a point here. Let's call this x prime. This is a point on the line, okay? Yeah? Then if I look at the difference between these 2 points, like that. So I have a line like this, right? This is the difference between the vector xn and the vector x prime. Yeah? Thus, the length of the line is the distance between them. Or if you just say the line is simply the difference between the vectors xn and x prime, right? Yeah? The distance between these two vectors. Now, our goal is still to find the length of the dotted line. Yeah? But then this dotted line would be simply you think about it as the sine of that angle, right? Or you can think about it as a projection of this difference onto the vertical direction. Yeah? The length of the dotted line is the length of the projection of this difference, xn minus x prime, onto the vertical direction. Yeah? So, and this is true for any x prime, yeah? X prime on L, let's say the distance between this point and the line is equal to length of the projection of this difference, xn minus x prime, onto the perpendicular direction. And to express the perpendicular direction, since we know that W is perpendicular, right? But we want to normalize it just to get the direction. We don't care about the size of the W, right? So just project it onto this unit vector, then we're all set, right? Yeah? That's how we express the idea that we want to. I don't know which far enough. That line there, projection onto the vertical direction. Yeah? Everyone okay with this? Yeah. And a bit of a analytic geometry and a little bit of linear algebra, right? Yeah. Then this is true for any x prime, okay? Any x prime. So we can write this, yeah? How do we express a projection onto a direction? How do we calculate projections? You take the inner product, right? Yeah? So we have inner product, the length of the inner product, so length of inner product, so this guy, this vector, this unit vector, transpose, yeah? And then multiplying the difference. Yeah? Okay? So, SVM, you see, we have a lot more derivation to do. In fact, we can take the whole week to do these kind of mathematical derivations, okay? There's a reason that it took people 40 years, from 1950s to 1990s, to discover this SVM. Yeah? Still not too bad, We are 30 years after that, so we're smart enough to understand all of this at the undergraduate level. So this is okay, right? Projection. Or you're taking the inner product as projection and to the length of that projection. Yes?
So what is x prime again?
X prime is just any point on the line L. Yeah? That's X prime there, right? Any point on the line, that's okay. Doesn't matter which point. Okay?
Thank
Yeah.
you.
Yeah. And
So basically, no matter which point we choose, we will still get like the distance from x and
yeah, this one will always be correct, okay? So now we're going to get rid of this x prime because we don't like this kind of arbitrary point, okay? So now the point is that this x prime is on the line L, right? So x prime is on L. What does this tell us? That means this x prime has to satisfy this equation for the line, yeah? Now remember this is the, without augmentation, right? That's why we write it as x transpose x plus b, yeah? Without augmentation. With augmentation would have been x transpose times x equal to 0 before, right? So now, without augmentation, this is the form. Now, x prime, when you substitute in it, it should work, right? So therefore, we have W transpose x prime plus b equals 0. Yeah, it's on the line. Well, what does this tell us? Why do we want to do this? Observe this here, yeah? What happens? We already have W transpose times x prime there, right? When you subtract that,
It will be 0 minus b.
0.
Minus b, sorry.
B, not minus B, not even minus, just B, right? You move this to the right hand side, negative of this equal to B, yeah? Okay, so therefore, the distance between any point to the line L is equal to simply now this transpose times xm, and then the W transpose times x prime part becomes this plus b, yeah? And then we take this norm outside of the magnitude because it's just non-negative, it's just positive because you put it at the bottom. Yeah, everyone okay with this so far? Okay. So this is the formula for the distance of any point to a line. Yeah, that's the formula. And notice again, this W is unaugmented, right? No augmentation, otherwise it will not work. For any point to the line, doesn't even have to be one of our data points, right? Any point will work. Okay? So that's the second fact. The third fact is that now we have to go back to, well, what if, now because we are interested in the data points, right? We can further simplify this, given that this data point has been correctly classified by this line L. go one more step. So if L correctly classify this point, then what happens? Well, we know from John, well, previous what we learned, and also from the midterm, 3 is equal to 0, right? Yeah? Again, just this is unrandom form, that's why we have this extra term b there. But it's the same as what we have seen in question number 1 in the midterm, right? Furthermore, we have this one is binary, so this one is in -1 plus 1, yeah? Either -1 or +1. That means what? I want to simplify number 2 there, right? That formula for the distance. So we have the magnitude of this thing to worry about. But if this thing is always greater than 0, what does that tell us? This magnitude, can we simplify this magnitude? Yeah, just yn times it, yeah? Yes. Yeah, just multiply your own sign, right? Yeah? You get the magnitude. Okay? Very good. Then finally we have, if we have a data point, xn, not just any point, right? And also the data point is correctly classified, then the distance between this data point and the separation line will be given by this. So, as I think I mentioned a long time ago that this other form is very important. Turns out that it gives you, in a way, the distance from the data point to the line. Yeah, and you have to normalize by this guy for sure. Yeah, but the most important part is really the numerator. So now we know the distance of each data point to the line. Now we can define the margin of the line, which is the minimum distance. Yeah, the nearest point to the line. What is that distance? So we define the margin of this line, or our separator or boundary. Let's say line or hyperplane. Which is a linear separator. Yeah. L. And we of course, we're under the assumption that it correctly classifies the point, so that we can use the formula under number 3, yeah, which correctly classifies all data points. Yeah. We're going to denote it by rho of L, like that, yeah, the margin of the separator L is the minimum among all data points, right? N goes from 1 to capital N, this distance, xn to L, yeah? Yeah? That's our margin. And of course, we can substitute that formula in there, in here, which is, this is yn, W, xn plus b, magnitude of W. Okay? So let me go back to make a copy and I'll come back here so you can copy if you have not finished copying yet. I just want to copy these 2 figures so you don't have to draw it again. So the margin for these 2 lines, the minimum would be the nearest point, right? So here, clearly this one, the way that I drew it intentionally, I drew this as the nearest one. And then this one is also the nearest one. But in general, the nearest point doesn't have to be the same point for different lines, right? So this one looks like this. And well, usually because the distance, so usually we draw symmetrical side as well for the margin. This one clearly has a factor margin, yeah, a bigger cushion for error. Okay, so inside those red bars, there should be no data point, right? Because this one would sit, the one that sits at the margin is the nearest one already, right? Yeah, inside there's no data point, yeah? So that's how we define the margin of the line, okay? And clearly then now we want to maximize the margin. If we say which we want to pick the best line, then we say the best line would be the line that gives me the biggest margin. Yeah, that makes sense? So that's exactly the goal of SVM. Find a separator, classifier, let's just say. That maximizes the margin. And it turns out that this is a difficult problem to do, right? Where the margin is minimum, right? So you're maximizing a minimum, okay? Max-min problems or min-max problems, they are known to be much harder than just maximum or minimum problems, okay? When you have this nested form of maximum, minimum, max-min and min-max, they are known to be hard problems. In general, they're very hard to solve, yeah? But fortunately for SVM, because of the structure, we have a solution to it that's pretty efficient. Okay, and we're going to explain how we solve this problem. We still need probably 2 more hours to explain how we can solve this problem. Okay, it's not non-trivial problem to solve. Next meeting. Okay. The first thing that we notice is that whenever we draw a line and we describe it by this W transpose times X plus B equal to 0. This W and B can be scaled any way we want. We still have the same line, right? We saw this before. You can scale the coefficient of your line any way you want. It's still the same line, yeah? Because the function is simply Wx plus B equals 0. Yeah? W and B can be scaled arbitrarily. So in fact, you have infinitely many W and B's for the same line. Yeah? And that's not good. We don't like that. Okay? We want to have a more unique representation of the line with just a unique W and B. Okay? And hopefully that choice of W and B that we use gives us an easy way to solve this max-min problem. Okay? And that goes to what the next calculation is the key normalization that we use in SVM to make it easier to solve this max-min problem. Okay? So key normalization, very important. So again, that's because we have many ways to scale X and B. Yeah? We want to normalize things. So first thing to notice is that again, we want this line to correctly classify all of the points. These 4 data points. That means we want Yn W transpose Xn plus B with 0 P for all n. Yeah, that's what we need. Okay. So clearly all of them will be strictly greater than 0. And then suppose the minimum one, because at the end we want to find this minimum on top, right? Minimum of this whole thing. Suppose you want to minimize the numerator, which is this product. Yeah. So we denote it by delta. It's the minimum among all data points of this product. Yn W transpose Xn plus B. Like that. Okay? Clearly this minimum will also be strictly positive. Yeah? Okay? But it can be anything in general. Yeah? And also depending on scaling, right? Because I can scale this W and B any way I want, you get a different delta. For the same line, right? For the same line. So that's not desirable, right? Yeah, we don't want that. So we want to pick, in fact, we only use W and B so that this delta equal to 1. Okay, we always scale this, normalize the parameters so that we have this delta equal to 1. So we're going to choose, always choose, I say always choose this. WB such that delta is equal to 1. Okay? Intuitively, we can do it, yeah? Because, again, we can scale W and B anytime we want, any way we want, we get the same line anyways, okay? Intuitively, it's possible to do it, but let's prove it. Let's prove that this is okay. So, the claim, our claim is this is without loss of generality. We do not lose anything by making this assumption that delta is equal to 1. Without loss of generality, or sometimes short for, very often if you read some books, it says WLOG, yeah? Like that. It's a very common term that we use in mathematical proofs to say, or in analysis as well, to say that, yeah, I'm going to force this delta. In general, this delta can be anything, right? But I'm going to force it to be equal to 1, specify it to be 1. But I want to make a claim to say that even though we specify it to be equal to 1, my solution is still general, can be applied to any delta value. Okay? This is without loss of generality. Or in the context of optimization, we are not losing any optimality by considering W equal to 1. Okay? We are not losing any optimality. Again, the idea is that, well, I can scale W and B anyway. I get the same line anyway, so I'm not doing anything that's strange by forcing W equal to 1. And I'm not losing the lines in my choices. Okay, but to properly prove it, yeah, let's just say, suppose your delta is not equal to 1 for some W and B. Yeah? Suppose the minimum is not equal to 1. What I want to claim is that I can redefine the line, the same line, by scaling W and B so that the delta is equal to 1. But I'm not changing the line, I'm still looking at the same line anyways. Yeah, that's the idea. So suppose we define a W tilde equals to the scale version of W by delta. So I scale this vector by delta, and then defined tilde B equal to B divided by delta. Yeah? It's okay because delta I know is strictly greater than 0, right? I can do this division, it's no problem. Yeah? Then what we know is that this L prime, defined by tilde transpose X plus B tilde, denotes the same line as L. Yeah? Same line or hyperplane, I just write line to save some effort as L. Right? Just scale by the same thing. No change, everyone agree, right? Yeah? Just divide by delta on both sides of the function. Now let's look at this L prime. My claim is this L prime, for L prime, the delta is 1. Yeah? For this one, the delta is defined as minimum among all data points, ym times W tilde transpose xn plus B tilde, right? Yeah, for this new line, that's the definition of the margin. Yeah, not margin, the delta, sorry. The minimum of the, that definition of that, yeah? So that's why I'm just rewriting that definition, yeah? For this, yeah. What is this equal to? It's a minimum, this one I can just copy. Here, this is 1 over delta of W, right? I just take 1 over delta outside. No problem, right? So I can take 1 over delta and then ym W transpose xn plus B, yeah? Simple algebra, right? just factor that 1 over delta out. Now I can take the 1 over delta outside of the minimum. Yeah? So I take it outside of the minimum. But now inside the minimum, what does it become? Inside the minimum is just minimum of that product, right? Just whatever that's on top there by definition of delta on top line. Yeah? So it's simply delta. Yeah, by definition. So this is equal to 1 over delta times delta equal to 1. Yeah? So done, right? So I have another representation of the same line where delta equal to 1. Yeah, again, L prime and L, they are the same line, no change, right? So basically I'm saying that I have a way to represent the same line such that delta is equal to 1. Basically, yeah? This minimum thing is equal to 1. Therefore, I think it's safe for me to always just simply assume that whenever I look at a line, I scale those parameters W and B such that delta equal to 1. Yeah? And that's without loss of generality. Yeah? Yes?
Sorry, how can we be sure that delta is not equal to 0?
Oh, because correct classification requires that you strictly within 0, right?
Oh, so we assume that it is correct. Okay.
Yeah, remember that's why we don't allow any point on the line right before.
Yeah.
Yeah, if it's on the line, we still say that's not correct. Yeah. Yes.
Does this only work if all points are classified, correctly classified? Or?
Yeah. Only works if it's a linearly separable.
Okay.
Yeah. So that the lines are all E equals 0. We're going to have a version of SEM where you allow some points to go across. Yeah. We'll talk about it. I think either tomorrow or next week. I forget. Yeah, when. Yes.
One question. Why is like tilde x plus b tilde
Mm-hmm.
equal to 0? Like for the third line of the proof?
This is, we just define this line in this way. This is a definition of the line L prime. There's no y. We just define this L prime as this line. Yeah? But it turns out that since it's all everything's just scaled by delta, right? It's the same line as L. You agree? Yeah? Any other questions about this? So it is a key normalization step, yeah? It's a key to make SEM work. Yeah? So instead of considering infinitely many choices of W and B, we always stick to a single choice for which delta equal 1. Yeah? Substantially reduce your search space for your parameters W and B, right? Yeah? So we limit ourselves to this case. And it's without loss of generality, so that's great. So therefore, our key normalization give us delta equal to 1, and then this tells us that rho of L after key normalization, the minimum distance, right? This is definition rho of L. Yeah, previously it's supposed to be delta over norm of W, right? Remember what this rho of L was defined as? Let me go up a little bit. Bear with me. Here, yeah? The definition of the margin, right? Rho of L is the margin of this line, defined in this form. But this form, you put the minimum on the numerator because it doesn't matter. The denominator is independent of m that you choose. Yeah? So the minimum of the numerator seems just our delta, right? So now we have normalized to 1. Yeah? So therefore now, after normalization, the margin is always equal to 1 over the norm of W. Yeah? Okay? After normalization, this is 1 over the norm of W. So, going back, this is equal to simply 1 over this. So now our job seems to be a bit easier now, right? Our objective is to maximize this one. Yeah? So we kind of no longer have a max-min problem, but you will see there's some new problem. So it's not so easy yet. The goal of SEM now becomes maximizing over W and B 1 over this. Yeah? But not yet. Yeah? We still have to make sure that our lines separate those points properly. Right? So previously we have to say we want to maximize this margin subject to the constraint that we have correct classification. Yeah? But now this constraints are normalized. Remember, I'm sorry. I know people hate this scrolling up and down. Yeah, I know you might get seasick, right? Even yeah. I do when people scroll up and down. I get seasick. So here, yeah, the correct classification has that requirement greater than 0. Yeah. So you have to add that one to the as constraint for your optimization. Okay. But then this one is without normalization. Yeah. Without normalization, this one basically says that delta has to be just greater than 0, right? Yeah. As long as delta is greater than 0, then we're done. But our objective now is after normalization. Therefore, your constraint also has to be normalized. You cannot just use this unnormalized form. Okay? So what is the normalized form of that? Well, the normalized form is that delta equal to 1. Or in other words, the minimum of those products equal to 1. Yeah, we have to put that in as the constraint. Okay? Yeah? This constraint of correct classification after normalization becomes the minimum of this product, yn times w transpose xn plus b, is exactly equal to 1. Yeah, no longer just greater than 0, but exactly equal to 1. Because that's our normalization. Yeah? Okay, so we have to put that in, which is subject to the minimum 1 that yn w transpose xn plus b.
Does this end up being like Chinese and Shannon where we have to like swap the two subproblems until we get to this?
Good thinking, but no, we have a better way to do this. That's why SVM is very nice. Yeah, you can prove optimality. Strict optimality will get at the end, okay? So this point, this last constraint, again, it's just I just put a note here, it's just a normalized form for correct classification requirement. Normalized version, normalized form, I guess, of yn plus b greater than 0 for all n, yeah, which is the requirement for correct classification for all data points. Yeah. So now we have this new form for the SVM. It looks a bit better than the previous one. Previous one we have max mean, right? Harder to solve. But then we are not totally home safe yet because we have a minimum here in the constrainer, which is shift some difficulty to the constraints part. Okay? So we still have to figure out how to solve a problem like this. And it's non-trivial. Okay? It will take us 2 more lectures tomorrow to get to the point to find out how we can solve this problem. Turns out that we can convert this to a very nice convex programming problem. And we know the convex programming problems can be solved easily by any kind of software solver. Okay? And you can solve it to global optimum. Okay? So yeah, that's pretty. I think we want to stop here because there's a lot more math to be done. We'll leave it for tomorrow. Any questions about anything? This or the midterm or anything like that? We have a few minutes.
When do we expect the marks to be back?
Yeah, the TAs have been working very hard over the weekend, but they could not finish yet. So we have to wait. I have not asked them for any prediction yet. Hopefully within this week. I don't know. Well, usually it's distance. The mark is really distance. Well, yeah, because you're only allowed to use part E, right? If you multiply something to E and then you're not using part E anymore. So, basically you convert it to a XOR, right? Then it's the same thing you have in the form you have. Right? Yeah, you get one. I asked TAC to get points, but you won't use all of the points if what you have is correct. But I forget what is 2 points you want to get.
So the weights always have to be according to
Yeah.
It's true that we demonstrate the weights. I just drew two line I shaded in the region.
Yeah, exactly.
So one of the points, there were like 3 different lines. I think we wrote the different lines.
Yeah.
So there were 3 different lines, 3 different versions of the perception that you just tried.
Yeah.
The validation.
Yes, so no percent of the relation.
At the end, so the third one, I wasn't able to finish it. So I went to the next question. I did the validation of 1 and 2. And then I said, if third is lowest, you choose that. If not, then you choose this.
You certainly should get some points for the first few.
Yeah.
The last statement, lower the better, I'm not sure how much it was worth. I depending on TA's mood, I guess I don't know. Sorry. Yeah. Yes.
I don't know how familiar you are with the data set, but
Yes.
when I did the implementation, there was an issue where, the smallest learning rate looks mostly correct, like we expect, like a curve slowly sloping upwards.
Okay.
But for the 2 intermediate ones, it is like, it just starts really, really high.
Yeah.
Is it this?
It does not ring a bell to me, so you probably have to ask this on Piazza so that the programming TA we can answer your questions to
Are
start.
we supposed to randomize, because the boilerplate code they gave us, they
Yeah.
don't randomize the weights. So every single time you run the data, it
Oh.
would run the exact same way.
Yeah.
Like, is the grass supposed to be deterministic? Is that like a